All right, a few minutes after the hour, we'll go ahead and get started. Hello, everyone, and thank you for joining us today. My name is Michaela McShane, and it is my privilege to welcome you to the T2U Innovation Series. T2U stands for Technology Transfer University, an initiative that helps NASA build relationships with innovative colleges and universities while introducing cutting-edge NASA-developed technology to students. This series features firsthand experiences and best practices from distinguished innovators and instructors at academic institutes around the country. These individuals have valuable perspectives about the educational benefits of bringing NASA-developed technology into the classroom. Please note that all audience microphones are muted and type any questions you have in the chat box. We will answer them during the dedicated Q&A section at the end. We also invite you to visit our website, NASA T2U website that'll be linked on the last slide for more information about this cool project. Today, we are joined by Matt Rappaport, co-founder and co-director of the Deep Technology Innovation Lab at the University of California, Berkeley, and several of his students. The UC Berkeley Deep Tech Innovation Lab is on a mission to unleash the potential of emerging talent and drive advancements in deep tech innovation. Collaborating with Berkeley Haas, Berkeley Engineering, Berkeley Law, and research groups across the campus, the lab provides an interdisciplinary, hands-on approach to solving complex deep tech challenges. I will introduce our speakers and then hand things over to them to tell you about their work. Matt Rappaport is the general partner of Future Frontier Capital, a pre-seed frontier technology venture fund. Prior to FCC in 2004, Matt co-founded IP Checkups, Inc., an intellectual property strategy and software firm where he managed hundreds of innovation projects for early-stage startups and large corporations. Caitlin Ryu is a Master of Translational Medicine candidate at UC Berkeley and UCSF with a background in kinesiology and biophysical sciences from the University of Toronto. Parth Patil is a mechanical engineer specializing in advanced energy technologies, and pursuing his master's at UC Berkeley. Megan Weatherston is a student in the joint UC Berkeley and UCSF Translational Medicine Master's Program. She holds a bachelor's degree in biomedical engineering and health sciences from McMaster University with a specialization in medical device innovation and entrepreneurship. Kavisa Shroff is a bioengineer with a strong interest in deep tech commercialization and early stage entrepreneurship. A graduate of UC Berkeley, she has experience in business development, market research, technology commercialization, and working with startups, research institutions, and corporate teams. Daniel Gonzalez is a Master of Translational Medicine candidate at UC Berkeley and USFC with a background in chemical engineering and biotechnology from the University of Berkeley. With that, I'll go ahead and hand it off to our presenters to tell you about their experience and their interesting program.
Thank you so much, Michaela. Nice to see everybody here. My name is Matt Rappaport, and I am the co-founder and co-director of the Deep Tech Innovation Lab at UC Berkeley. So I'm just going to give you a little bit of background on what we are and what we do, and then I'm going to hand it off to my colleague Kavisha, who is a mentor in our program and also a graduate from our program. So can you go to the next slide, please? So the Deep Tech Innovation Lab has been around since 2021. We've been providing this unique curriculum at UC Berkeley through the Tusher Strategic Initiative for Technology Leadership at the Haas School of Business. And in a nutshell, we combine education and research to help bring cutting-edge technology to the market and society. Next slide, please. So a lot of times we get questions about what is deep tech. So I always like to sort of set the stage. We spent a lot of time thinking about it, and we came up with this basic description or definition, which is deep tech refers to disruptive innovations built on scientific discoveries that transform industries, require extensive R&D, involve significant intellectual property, and solve complex problems that conventional technologies cannot address. Next slide, please. So here's a handful of some of the technologies that we think of when we think of deep tech. So artificial intelligence, advanced manufacturing, brain-computer interfaces, autonomous systems, quantum computing, advanced materials, and so forth. Next slide, please. So at the we've essentially created this program. We have a fall program and a spring program, and we work with several academic partners. Specifically, we work with students from Berkeley Haas, graduate students from Berkeley Engineering, as well as Berkeley Law students. And we have those students work in interdisciplinary teams on projects that come from our innovation partners. So here are a few of our innovation partners on the right side of the screen. You can see Lawrence Berkeley National Lab, Hewlett Packard Enterprise, Sahlgrenska Science Park in Sweden, and then of course NASA. And this was the first year that we worked with NASA technology. It was super exciting, and we're really happy to be partnered with them. Can you go to the next slide? I just want to pay respect to my team. These are all the people that support our program and help mentor our students. So myself and Bo Hayden are the founders of the lab. Wayne Stacy is the head of the Berkeley Law and Technology Center at UC Berkeley. My colleague Leah Edwards is on the faculty at Berkeley Engineering. Kavisha, who's on this call, is a graduate from our program and also one of our team mentors. Victor Strom recently got his PhD in deep tech innovation and entrepreneurship from Chalmers University in Sweden. And then recently we had Chang join us. He was a student in our class last semester, a law student who has also started up his own company, and he's joined us as a mentor for this semester. Next slide, please. So at a high level, we teach students from interdisciplinary backgrounds how to assess competitive technologies, analyze IP, intellectual property, and regulatory issues, and explore commercialization opportunities for real-world deep tech projects. Next slide, please. Our goal is to develop T-shaped students. So in our classroom, we have about 70 to 75 students each semester. And what we're trying to do is develop these skills around their core sort of interest, whether it's engineering, business, or law, and then also build out the horizontal part of the T with these different disciplines so they can understand and communicate across disciplines. So a big part of our program is to help students learn how things work in the real world when they get into a company, or if they're starting their own startup or working in a consulting field. Just understanding that intersection of sort of business, technology, and intellectual property is very helpful for students to kind of see the big picture. Next slide, please. So we talk about in our program a lot about technology and business, and then IP, which we sort of talk about as control. So we think of it that you may have great technology, and there's this overlap with how it fits into the business and commercialization side. And so we spend a lot of time working on what is this technology, and then how would we be able to commercialize it? But ultimately, if you don't have the ability to control it, then how do you stop others from coming in and copying you? So this is how we spend quite a bit of our time in the semester teaching frameworks, and Kavisha is going to walk you through some of the details of our program. Next slide, please. These are the core questions that we want the students to answer. So the first is, what is the technology that we have? And of course, with deep tech innovation, we're often seeing very complex technologies. We don't require that the students have a background in the technology area. We actually prefer that they're just interested in it. So several of our students today are Masters of Translational Medicine students at UC Berkeley and UCSF, and they focused on technology that was either tangentially related to that field in one case, and in another case was completely separate, more focused on the energy and climate area. So the ideal situation is students have to figure out, how do I learn about a new technology, and really go through this discovery process for a deep tech innovation to figure out what is it that we actually have. Part of that is also understanding what are the core assets or the things that differentiate us from what other people have. And so that leads to this next question is, how does what we compare, or how does what we have compare to others? Is it better than what competitors have? Is it very similar? How is it different? And then finally, we ask the students to figure out who will pay for it, or how will it generate value? And these are the three core questions that we try to answer with our students and with our projects, so that when we report back to our partners at the end of the semester, we can give them answers to these questions. Is this technology actually commercializable? How does it differ from what others have? Is it better, faster, cheaper? And is there actually a market here that we can go in, and how would we do that? Next slide, please. So another big part of our program is customer discovery, and reach out to lots of experts in the field. They could be technical experts, they could be business or marketing experts, they could be inventors of technology, they could be intellectual property or patent attorney, all types of different experts. And part of the goal of our program, that's maybe a little bit different from some of the other customer discovery programs, is that we want our students to really understand what the technology is, because these are disruptive technologies, and it's really important for them to have these conversations with some of the world's foremost experts in these areas. We want to make sure that they have a really good understanding. So we spend a lot of time focusing on the students really getting a good handle on what they have. So we use this quote to show the students that, hey, it's really important not just to understand, what people want or what they're asking for, but to understand the bigger picture of how this fits in. So I'm going to pass it to Kavisha now to take you forward a little bit on how the structure of the program works. Thank you.
Thank you, Matt. All right, so now I'm going to walk you through what our program looks like and walk you through each step of how we're enabling our students to kind of participate and work with the projects. So this is a general overview of the program, and then in the coming slides, I will walk you through each of the part and then showcase how we really do it. So when we get started in the semester, we introduce the students to about 20 technologies. Now, these are deep tech early commercialization technologies that are coming from our partners. And then we ask the students to rank them according to their order of interest. The technology overviews that we're presenting, they are just a little bit about what the technology is about, the technology space, the industry. And then we let the students be intrigued by them and let them rank. Now, one big part of this program, which is different, is that the teams that we're forming are super interdisciplinary. These graduate students are coming from Berkeley Haas, Berkeley Engineering, and Berkeley Law. So a typical team would look like 2 engineers, 2 business people, and a lawyer working together for bringing in their interdisciplinary perspectives to work on their technology. One big part of this class is helping them identify technology and the patents. So we give them all the published scientific papers and patents that were provided us by the technology transfer officers. And then we equip them with tools and frameworks that can help them understand, read the patents, and derive valuable information from those patents to get started with their analysis. And this is what early semester classes look like. We put a lot of focus in having open communication, so we ensure that there is communication laid early on in the semester with the tech transfer offices, the PIs and inventors of the technologies, so that the students can understand what the commercialization scope was that was envisioned by the TCOs, and kind of get an understanding of what relevant pre-work has already been laid and what they're expecting out of this whole program. We also encourage the students to have regular check-ins with the TCOs to provide timely updates and have them have any recommendations or guidance that these experts might have. Now, to give you a sense of what we really teach in the class, these are frameworks which analyze deep tech innovations from a variety of perspectives. Like our class, we have different expertise people. We try to focus on each expertise, and then frameworks like tech trees, technology assets, helping them map what the technology looks like from a pattern landscape, but also from a value chain aspect. We help them identify market segments and identify what that really means. So to give you an example, this is what a technology landscape looks like. So we encourage the students to identify what are the key assets of their technology, help them lay out and identify what from those could be their tech assets, what might be the ones that can help them further analysis, what are the ones that they want to focus, or what are the ones that help them establish some sort of competitive edge. Throughout the semester, we have exceptional experts from business, tech, IP, like regulations come. Every week we have about one speaker that comes and talks about how their unique expertise fits into this innovative ecosystem that we're building, and their expertise in terms of how is that relevant in the deep tech commercialization space. The photo that we see here is from our interim presentations. We have had about 15 to 20 guests, experts from the industries who came and evaluated the students' analysis and work so far up until the interim presentation. So like you can see, we're kind of building a very collaborative, creative environment where there's a lot of interdisciplinary work, collaboration, and communication. So to move on and kind of sum up what we've talked about so far, and going back to what Matt said about the core questions, the entire class is focused on helping these teams identify the core questions and answer them. So what do we have? Why is it better than what the competitors have? And who will pay for it? And all the analysis, frameworks, and tests that we equip them and teach them and encourage them to go find out are to answer these core questions. So for instance, what do we have by enabling them understanding the technology feasibilities, like the IP readiness, we're helping them answer that question, and then so on and so forth. So this really captures the gist of what we really, what this whole program is about, equipping these students to identify these core questions for their deep technologies that they're working with. And they get a lot of time throughout the semester to come and talk about their progress. It's a great opportunity for them to actually come on stage and talk about these complex findings and find their way to present it to a variety of audience. So towards the end of the semester, they culminate all of these analysis and put together the market research from customer discovery and their other analysis. And most importantly, they highlight how these insights can provide different market opportunities and their strategic recommendations based on their findings to the tech transfer officers and the PN inventors. So at the end of semester, there's a big presentation with each team and tech transfer offices, and it's a conversation where they talk about all of these things, chance for the tech transfer officers to understand any questions they have, and it's just kind of really nice. And then to the end of the program, we do this incredible event. We had this one in December last year, which was called the Deep Tech, Emerging Deep Tech Trends, and each team presented findings and interesting market opportunities within their technology space. And this was an event where we had researchers, investors, deep tech enthusiasts from around the Bay Area. And we had like poster presentations for like a really good discussion going around. So this is our entire program. I hope it helped. And then we can go on to the two teams that we had last semester, and they can talk about their specific projects.
Yeah, thanks, Kavisha. So hi, everyone. My name is Megan, and today, alongside my colleague Parth, we'll be sharing our experience working with the NASA Tech Transfer Office on our project on commercializing one of their patented technologies, which was a solid-state CO2 sensing device. Next slide. So we worked on this project with 3 other UC Berkeley students, and we were guided by mentors Victor, Matt, and Kavisha, and we had guidance from Jay Singh at the Tech Transfer Office. And so to start, I wanted to go over our overarching goals for this semester, and this was to understand the commercialization strategy. We were guided by 3 major questions, which were, what is the problem that the tech we were given is actually trying to solve? How is the technology better than competing solutions? And for which application is our technology actually best positioned? And so to help us in our endeavor to answer these questions, Matt and our mentors at the Deep Tech Lab, they taught us a bunch of different tools that we could use, and I wanted to highlight 5 of the major ones. And I'm going to refer back to these tools as we go through some of the details of our project a little bit later. But yeah, so starting on the left, we started by learning about techno-economic analysis as a method of assessment. And this includes a combination of understanding the technical feasibility, but then also the economic viability. So this includes things like process modeling, block diagram development, market analysis, and identifying scalability. And yeah, so this was really important when specifically understanding the use case of our product, as some markets are less economically crowded than others. And so the next assessment that we did was patent landscape and IP position. And this was really interesting, especially for the engineers and business students who had less experience with law. And so I just wanted to highlight one feature from this as someone with more of a background in academic research, and that's the value of systematic patent searching. This is essentially a Boolean search within a patent database, and the output is a set of patents that aligns with your desired criteria. This can provide information like the types of companies that have patents in the areas specifically, and the tool that we used was called lens.org, and it provides a bunch of insights that were really useful for our analysis. And so next we learned about tech asset and tech tree mapping. During tech asset modeling, we broke down the sensor into its core technological components to understand their performance, their costs, their value, and then moving further from that, tech tree modeling helped us with a representation of how all these technical features interacted in a broader ecosystem. And so after understanding all those technical components, thinking about the even broader value chain mapping was really useful to identify what dependencies the sensor has and what technologies are actually dependent on the sensor. And so seeing where our sensor fit in and comparing this to other products that fit in similar value chains was really, really helpful for informing the actual market for our technology. And lastly, just some more traditional business analysis methods like TAM, SAM, SOM, and SWOT helped us kind of quantify the value and assess some of the risks and opportunities for our project. And so to demonstrate the actual application of all these frameworks, we wanted to take you through some of our findings, which we presented to the tech transfer office. And so these slides, which I'm about to show you, are a representation of running through projects like this, which start from receiving a patent and end with a market recommendation. And so, as I mentioned in the guiding questions, understanding that the problem that the tech is actually trying to solve is really, really critical. The problem that our tech aimed to address was that existing CO2 sensors face significant limitations in functionality, adaptability, and accuracy, making them really unsuitable for diverse environments. And just noting the yellow box in the top right corner, we wanted to emphasize the frameworks as we go through our findings, so that it's really clear how the tools that we learned actually provided to our analysis. And so to start, the technology had functional advantages. There's a basic representation of the tech in the bottom left of the screen, and it essentially consists of carbon nanotubes doped with a metal oxide that causes the electrical properties like resistance and causes a signal to change with CO2 exposure. And because it's solid state, the sensor had no moving parts, making it compact, durable, and it's able to operate in really extreme environments. And so based on our understanding of all these technical components from patent, literature searching, we charted those design advantages, as you can see on the right here, and we compared them to traditional sensor types, which all seemed to lack capabilities that the NASA sensor did not. So we then had to figure out how we could actually leverage all of these tech advantages in the application that we wanted to explore. And so there were a bunch of applications we identified initially. Systematic patent searching was really important here because it could show us all these fields where CO2 patents exist. And we were then able to narrow it down to 2 specific areas. Next slide. And that was agriculture and healthcare. And this was done through both mapping the functionality and utility, but also, again, systematic patent searching, because we wanted to select areas where they weren't already oversaturated with patents. And so we were then able to narrow it down to just one field, and that was healthcare. And that was done through various techno-economic analysis, asset identification, and value chain mapping. And so going a little bit more into detail into this, we identified that healthcare aligned the most with the functional advantages, but we then wanted to figure out what applications could actually address those 2 remaining tech assets, and that was low power consumption and variable environmental functioning. And yeah, so it seemed that CO2 measurement devices for harsh environments would be a good area to explore. Next slide. So customer discovery interviews, as mentioned, they're super critical along the entire way, but specifically once we identified the field that we wanted to contact professionals in, we could ask really targeted questions. So we then identified 2 specific applications. The first was improving emergency medicine with capnography devices, which are essentially these CO2 exhalation measurement devices, as well as ambient sensing in enclosed spaces to prevent associated health issues from CO2 buildup. We spoke with professionals, and it seemed that the capnography application was actually limited because of the functional capabilities of our sensor, and we spoke with the inventor about this. And from all these conversations, we then came up with the conclusion that ambient CO2 sensing was the primary market. Next slide. So as mentioned, business analyses were super important because quantifiable data is really compelling, and it's a core component of defining that market potential. And it seemed that there was significant growth for our sensor in this field moving forward, looking forward to 2030. And again, as you can see on the right here, you're constantly considering the context in which this technology actually exists. And if you're providing values, you're really trying to assess and justify why you're providing these values. And so based on our assessment, we suggested to the Tech Transfer Office that immediate exploration of ambient sensing was the ideal commercialization strategy, but further research into expanding those actual technical capabilities could open up the market to a variety of further opportunities like capnography. And as mentioned, we presented these findings at a final presentation with NASA and concluded it as well with that final industry night with other teams from the Deep Tech Lab, as well as the team that you're going to hear from after this. And so summarizing this process, it started with understanding the problem, looking at our patent, looking at existing patents, and figuring out what exactly are the interesting applications, the market potential. From then continue with specific targeted user interviews, figuring out what the licensing strategy should be, and then making our recommendation.
So from the support we got from beyond the UC Berkeley's Deep Tech Lab Innovation, we got support from the Tech Transfer Officer from the NASA, that is Mr. Jai Singh. He gave us licensing information about how we can strategically give the licensing to the product, whether to go for non-exclusive or exclusive licensing. And also he made us to connect with the inventor of the sensor, providing us with regular feedbacks and on the analysis and also some recommendation onto the strategy. And meanwhile, we also got some guidance from our inventor as well. They answered us from some technical questions regarding about the technological understanding and help us to move away from the capnography focus which we were having at the initial start of the project. So next slide, please. And also leveraging different team backgrounds, as I'm from an engineering background, so I had little experience with business and the law area. So interdisciplinary team gives us an opportunity to have a diverse critical thinking capabilities and also gives a streamlined solution to a problem. Next slide, please. And focusing on to the challenges, first challenge we face is all about navigating through new information, as many of us never had such deep pattern analysis. So it was completely new for us. So we were trying to understand how it is working. Second challenge was about choosing a direction. As the sensor had lots of application, so it was very hard to narrow down one complete application which can be aligned with the advantages that the sensor had. Third challenge was about the effective communication. In this part, we learned about how to prioritize the information while asking the questions to the inventors or the expert interviews. And the fourth challenge which we faced about is conveying the information to different interdisciplinary background people, because it was very hard to explain in technical aspects or engineering technical aspects to a law student or a business student or a medical student. So it was a learning about how we can convey the message or the information to the team. And the fifth was about iterative research, as we get lots of information and sticking on to one focus is not an option. we have to like be open-minded to the new source of information as well. So it requires a lot of iterative research as well. And next slide, please. And from my experience, I learned about collaboration skills, like as working with diverse background people gives me about like an insight about how does the industry works with the technology and into the market area, and also about understanding about how does the technical aspects and the market aspects align together with IP and the patent works which are essential for the industrial domain. And third was about like also getting an insights about future innovation applications, just like our sensor was based on like semiconductor device thing. So it is able to get like doped with different materials, and with that we can change the application domain as well with the sensor. So it was like a bridge for research and industry, enabling like complete solution for advanced innovation to that particular technology.
Yeah, and then in terms of my experience with this, so after this year, I plan to pursue a PhD and eventually medicine. And there were three major impacts that I've already noticed and will continue to bring to my career. And the first is this idea that patents and IP have so much technical information and the potential to be used for really strategic market positioning. This isn't something that's talked a lot about in my experience of academia so far. So gaining a new source of information has been really exciting. And then next, we did a lot of user interviews and customer discovery. So my comfort with these conversations and the connections that I've been making have been really significant. And lastly, it's just been really interesting to see the different motives for actually commercializing technologies, because we're usually looking at this from the point of view of the entrepreneur or the licensee and not the actual researcher or the inventor. So overall, project was super different than any of the work that I've done so far, but the interdisciplinary collaboration, as mentioned, is just super enjoyable. Next slide. So yeah, thanks everyone for listening. We've linked our contact information here. If you want to reach out on LinkedIn, scan the barcode. We'd be happy to chat further about anything.
Thank you so much, Megan and Parth. I think our next team is ready to go. Danielle and Caitlin.
Yep. Yeah, we're ready. So I'll begin with introducing both of us. So yeah, hi everyone. Yeah, thanks Megan and Parth for presenting. That was awesome. So now, Caitlin and I, we're going to be presenting our experience with working with another NASA patented technology. Specifically, we're looking at what's called COBRA, which stands for a Comprehensive Oculomotor Behavioral Response Assessment. Next slide, please. So through our commercialization strategy development, similarly to the prior group, we also sought to answer three main questions. The first one was, what is the problem the technology is trying to solve? The second is, how is the technology better than the competing solutions? And the third is, for which application is this technology best positioned? So we first evaluated the technology using the scientific literature and patent applications that were available to us, after which we met with the technology portfolio manager, the TCO office at NASA, and the original inventor to answer some of our unanswered questions. And to also gain some insight onto the intended uses for the COBRA technology. After which, we then leverage our strengths as a multidisciplinary team of law students, engineering students, MBA students, to then narrow down this target market using stakeholder and customer discovery interviews, competitor analysis, IP analysis, as well as market analysis to ultimately come to a final recommendation and a path for successful commercialization and adoption. Next slide, please. So in terms of the technology, Kaylin will be introducing us.
Yeah, so like Daniel mentioned, we first sought out to understand the technology and found that eye movements have long been an indicator of significant sensory motor deficits caused by tumors or other severe brain pathologies. What the COBRA technology is able to do is generate a validated test of eye movement biomarkers for the detection and characterization of a wide array of mild impairments of neural function. Next slide, please. COBRA has been validated in 3 specific use cases, which include testing the effects of alcohol, sleep deprivation, and early detection of subclinical functional impairments from treatment side effects that will allow physicians to adjust or stop treatments before irreversible damage occurs. From these studies, we have gauged some advantages of the COBRA technology as being non-invasive and user-friendly, as well as being instantaneous and providing objective results. The tool requires minimal training from the administrator and does not expose users to invasive procedures, and it only takes approximately 5 minutes to yield highly sensitive and specific results from a series of dynamic eye movement biomarkers. Next slide, please.
So to begin, to prepare before meeting the NASA TCO inventor, we first looked at the information that was provided to us. So on the right-hand side of the screen, there was a series of 4 publications which ranged as far back as 2017 up to most recently of last year of 2024. It's important to note that the original inventor was on the 2019 publication. And then we also looked at 4 patents that were shared with us as well, just to kind of get an understanding of the IP strength, as well as to understand the different technologies that are covered. Once we then met with Dr. Leland Stone, who was the original inventor, as well as Jay Singe, who was our connection at the TCO office, we learned a few key learnings and clarifications. So the first one was that the core value of COBRA is excelling at detecting subtle functioning impairments before structural changes. So this is really emphasized in their 2024 publication, and primarily through the comparison to an individual baseline for very high specificity. So this kind of helps us focus our application of wanting to look at markets where we could look at monitoring changes and readiness rather than focusing on an initial diagnosis, for instance. And because this high sensitivity was validated, it really led us to consider a lot of different markets that weren't apparent at first glance. Another takeaway that we had was that there's a significant hardware gap, at least at the moment, where there's a requirement for a more robust and field deployable device. This was envisioned in their most recent patent, but we were primarily looking at the market for the software and potential implications with a field-ready hardware device that could be deployed later down the line. So once we combine this, and then we were able to verify some of the patent information. We also learned that the NASA patents, they really help to protect the unique COBRA analytical methodology. And specifically, they look at the specific impairment vector analysis. So it's not just common oculometrics like any eyewear device, but really specific numerical analysis that is incredibly powerful. And because they have patents dating back many, many years, they were at the forefront of this beginning IP trend in terms of neurological patents and eye tracking devices. Next slide, please. So essentially, our strategic impact, what we got from our initial meeting with both Leland Stone and Jay Singe is that we were able to confirm COBRA's unique value and begin to refine our market focus, highlighted by the critical hardware development need for field use, and validated the strength of the patented and analytical methods. And this really helped us determine who we'd want to interview and have customer discovery interviews with, which Kaylin will now talk about. Next slide, please.
Yeah, so after our TCO and inventor meeting, we collectively decided to narrow our focus down to 4 main industries. Although the COBRA technology is useful in a variety of settings, we felt that these 4 industries reflected the most viable markets. So we reached out to stakeholder and end users to conduct customer discovery interviews. We would start the interviews in a solution agnostic manner to understand the true pain points in their workflow, and then present the solution to gauge their interest and feedback. 31% of our interviews were clinical and sports concussion specific, 23% of our interviews were within the DUI assessment sector, and 15% of our interviews were with military personnel. These interviews and personal testimonials were pivotal in choosing our final market as the DUI assessment tools. We found that the price, the type of impairment that the technology is assessing, current gold standards methods in the industry, and technology readiness were key factors that would drive adoption. Next slide, please.
So now on this slide, I'll be contrasting the different market opportunities along with the key barriers across 3 potential sectors, primarily healthcare, sports, and military and aerospace. And If you click on the slide one more time. Okay, perfect. You can see that there's an arrow at the very top that goes from saturated to emerging. So this is kind of our process of breaking down everything. Primarily in the healthcare field, it's quite saturated. There's a lot of opportunities of early impairment detection, but you have major risk from navigating complex FDA regulations, extensive clinical validation, incredibly difficult hospital workflow integration, as well as HIPAA compliance and high competition. So the entry is very resource intensive. Now, when we look at sports performance and rehabilitation, which is semi-saturated but also semi-emerging, we see that sports really provides focused opportunities for looking at concussion assessment. But here we also see some of the key risks involve kind of proving the field reliability, which has not quite been proved yet. Also ensuring athlete compliance and engagement, as well as data privacy. So it's potentially faster than healthcare, but also requires quite a bit of practical validation. Now, lastly, when we look at military and aerospace, now this has a very high stakes applications, such as like readiness assessment, trying to improve mission safety. But the current significant risks in this field are the fact that there's quite stringent hardware and hardware requirements, as well as security protocols, and just the complexities of navigating long funding cycles, and which could slow adoption over time. So from these three sectors, they all have their own opportunities, but also very distinct challenges, which is why we actually wanted to focus more on the DUI market. So next slide, please.
Yeah, so after narrowing it, there we go. After narrowing it down to the most feasible market, we revisited the patent to conduct an intellectual property landscape analysis for eye tracking tools used in DUI assessment. This initially posed a challenging learning curve, but with the help of lectures led by Matt Rappaport and leadership within our multidisciplinary team from the law student, we were able to gain valuable insights into the patent landscape. Upon first glance, we found that the patent landscape for eye technology tools in DUI assessments has seen significant growth, with publications rapidly increasing over recent years. This rapid increase reflects growing competition and innovation in the market. However, NASA's strategic move to secure a divisional patent in 2017, followed by continuation in part filings in subsequent years, places COBRA in a unique position for several key reasons. First, by filing early, exclusive rights to critical aspects of the technology are established. Securing these patents early enables an early mover advantage, creating a barrier to entry for competitors and protecting this innovation from infringement. As the market grows, NASA can also continue to leverage the intellectual property for partnerships or licensing deals. As well, the CIP filings allow for inventors to build upon the original patent by adding features or improvements without losing priority from the initial filing. This means that although the CIP filings may include new developments, they are still tied to the original 2017 filing date, and it ensures that NASA maintains the early mover advantage over others who may have filed in more recent years. In essence, the early patent filings have offered the ability to control and shape the commercial landscape as it evolves, which allowed our team to then consider the competitor landscape of existing technologies on the market. Next slide, please. Our approach to the competitor landscape analysis was highly iterative. Not only did we find competitors, but we also went deeper into understanding some of the gold standards in each of the industries. For DUI assessment tools specifically, we found methods that law enforcement and regulatory bodies recognize as reliable and accurate, and also some technologies that are in development. With our multidisciplinary team, we focused on identifying what makes these tools successful and what gaps COBRA could fill. This included technical performance as well as usability and scalability. Of the court-admissible tools, which include blood and urine tests, evidential breathalyzers, and standardized field sobriety tests, we found that this roadside testing protocol in these standardized field sobriety tests to be entirely subjective and time-consuming. Next slide, please. So standardized field sobriety tests require police officers to conduct 3 behavioral tests with no real objective endpoint. We met with an officer at the UC Berkeley Police Department who walked us through what the typical procedure would look like, and he emphasized how much more efficient and accurate a device would be compared to these tests that are subject to human error. Next slide, please. Other court-admissible tests currently include evidential breath measurement devices, which require regular calibration to meet strict accuracy standards and are typically used in more controlled environments such as police stations. As well, drivers can actually refuse this in some states and opt for blood and urine tests, which have their own limitations. While blood and urine tests provide highly accurate measurements for alcohol and certain drugs, they give only a snapshot that may not reflect the driver's current level of impairment. Additionally, these processes are invasive and require time to be processed in a lab, making them less effective for immediate roadside assessments. There are non-court admissible devices on the market as well, which include consumer, preliminary, and THC breath measurement devices, and these devices tend to be less accurate and reliable. COBRA fills these critical gaps by offering a non-invasive, real-time solution that addresses the limitations of traditional methods. COBRA offers instantaneous, actionable data for potential law enforcement in the future, allowing for more reliable and timely decision-making. Next slide, please. With its ability to measure impairment from both alcohol and drugs, COBRA positions itself as a powerful tool in the growing field of DUI assessment, giving law enforcement an objective, accurate, and scalable solution for impairment detection. Can you click one more? Thank you. By overcoming the limitations of current technologies, COBRA could be a game changer in ensuring safer roads and more effective law enforcement practices. Next slide, please.
So yeah, just to kind of recap the market, it's a $1.8 billion total market, which might sound small, but it's still significantly growing. We estimated that the continuous annual growth rate would be around 15%, which is in part because of a few reasons. Increasing cannabis legalization creates a very urgent, unmet need for objective roadside drug impairment detection technology. Also, current subjective tests like field sobriety tests kind of suffer from reliability issues and potential bias. And COBRA is really targeting a substantial market opportunity here because of their incredible IP presence, which gives them a first mover advantage. So by addressing this critical gap of a focus on validation, legal admissibility, and training, COBRA is very well positioned for a strong growth within the significant market to ideally get the SOM of around 200 million after a few years. Next slide, please.
So our final recommendation is to explore the immediate opportunity to penetrate the DUI assessment tool market. Upon further developing a handheld portable COBRA device, this prototype could be used to penetrate the market across police departments in each county. Later, integration with the DMV for individualized baseline evaluation at the time of driver's license registration would allow the tool to be seamlessly adopted into the existing workflow. This initial investment in a use case with a strong pain point can prove the operational readiness of COBRA that may allow for expansion across use cases. These use cases may involve a licensing agreement for joint development of a robust and portable device that could be used in the military, or offer value-based pricing that may drive adoption by clinicians and researchers within the fields of ophthalmology, neurology, and athletics. Through the Deep Tech Commercialization Strategies course, we were able to deliver a thorough analysis on the go-to-market strategy, incorporating real stakeholder feedback and guidance from industry experts. Our multidisciplinary team leaned on each other's strengths and worked together to expand our knowledge across the various disciplines, delivering this final recommendation to NASA at the end of last semester. Next slide, please.
Yeah, so in short, my work on this project, specifically COBRA, was really key in teaching me how to translate complex science into practical real-world solutions and applications. And it kind of really showed to me the necessity of aligning technology with both user needs and be able to integrate engineering, business, and legal strategies to help improve safety and health outcomes. And it was such a joy, actually, just to work with people outside of my major, coming from an engineering centric mind first. And as a whole, I feel like I really just learned a lot of skills that I'm still beginning to apply with other classes and projects that I've taken on since. Next slide, please.
Yeah, so to echo Daniel's experience as well, through this experience, I gained insights into the commercialization process and understanding the different motivations between the inventors, stakeholders, and ultimate end users. And I particularly valued the opportunity to work with an interdisciplinary team of engineering, law, and MBA students, where the collaboration helped me to identify my own strengths and weaknesses while simultaneously enabling me to expand my own expertise in unfamiliar areas. This has given me the practical skills to bridge the gap between research research and industry, empowering me to drive impactful solutions, not only in this field of deep tech, but within my own studies as a Master of Translational Medicine student. And I hope to apply this newfound knowledge as I move into industry roles in the future and continue to build this T-shaped interdisciplinary mindset that is really important for commercialization and successful adoption from the market users. Next slide, please.
So yeah, our final slide is just an image of the whole group. This is everyone that we had the pleasure of working with, and that is our presentation.
Okay, there we go. All right, thank you so much, everyone. That was so interesting and informative. We have quite a few questions, so we'll do our best to get to as many as we can. And if we were not able to answer your question in the couple minutes that we have left, we will follow up with you via email. So don't worry if you don't get your question answered right now. I'll go ahead and just ask the questions as they appear in the chat, and whoever wants to take them, go ahead. So to start, what has been your most successful transfer of knowledge from the lab to applied functionality in the field?
I'll take that one just briefly. You know, we've had a lot of technologies that we've reviewed over the last several years. Many of those actually we've determined through the students' assessment that they're not actually commercializable at this time, and we're always making recommendations to the PIs and the tech transfer officers of how they could drive the research in a different way. There have been a few technologies that we've worked with that have turned into startups and turned into commercialized technology. And so, you know, certainly we look to those because they're the easiest things to say, oh, look at how great our lab is doing. But to be honest, I think the students are doing such a deep assessment, and to be able to go back to the providers, the technology providers, and say, hey, you know what, this is a little bit too early, or there are other technologies that really are more effective or better, faster, cheaper than this, or here's a different direction you could go. I think those are really valuable outputs as well. This is a big part and mission of the Deep Tech Innovation Lab to make this process of commercializing deep tech innovations more efficient. And so typically we sort of don't point directly to the wins, because we think that there's lots of wins that come from this deep analysis for these tech transfer offices and the PIs to kind of guide their research going forward.
Thank you. Okay, what are the different types of metrics, quantitative and qualitative, that used to assess program effectiveness? Did I read that right?
Yeah, so I mean, look, we rely on several, like from the organizer's perspective and the director of the lab, the first and most important thing is that our students are getting an excellent learning experience and that they're working on these interdisciplinary teams and getting a lot out of it. At the same time, we want our partners to, you know, give positive feedback on the depth and quality of the research that our students are doing. So in those final presentations, we listen in, myself and our mentors, and we hear lots of feedback from incredible PIs that are experts in these areas saying, wow, you've really opened my eyes, you've exposed me to things I've never heard before. And there's this sort of feedback loop where the students realize how much they've learned throughout the semester, how much they've benefited from this program, and how much they really are experts in these areas. And then, of course, the PIs and the tech transfer groups are also seeing, you know, look at how far this technology could go. So those are some of the more qualitative metrics. On a quantitative side, we look to things like, you know, does this technology make sense to commercialize? Should it have been patented in the first place? How can we help drive faster and more efficient commercialization of deep tech innovations? And then, of course, those that turn into startups and end up making an impact in society through jobs and through revenue creation and new technology that helps make an impact. Those are also sort of more quantitative metrics.
Awesome, great. Let me see. What would you say is the greatest benefit that you received from participating in this program? I know some of the students touched on this in their testimonials at the end, but if anybody wants to add anything kind of to round out that section, go ahead.
Oh, how about I'll pick, how about Caitlin? You.
Yeah, so I think in addition, I feel like I can't say interdisciplinary enough, but in addition to working with these teams who really do help identify what your own strengths are, but also leaning into your weaknesses, I really enjoyed just getting exposure to so many different types of deep technology that I otherwise wouldn't have throughout my program at the Master of Translational Medicine. And being privy to some of the patented technology and some that are in the process of being patented from Berkeley Innovation Labs has been a really beneficial experience for me as a student who has come to UC Berkeley to gain this wider lens and a bigger understanding of the technology that's out there in the Bay Area as well. So I think I can't pick the top one, but I think the two most beneficial experiences that I've gained is that I was able to really learn more about myself as a professional and as a student, and also to be able to learn so much more about deep technology in fields that I'm unfamiliar with.
Awesome, thank you. We are just about out of time, and I think that's a great place to end. So we'll go ahead and say thank you, everybody, for joining. I hope that you found this valuable. I know that I did. The recording of this webinar episode will be posted in a couple days, so you should get an email about that. And if we didn't get to your question, we will follow up with you via email also in the coming days. So thank you all. I really appreciate you taking the time to come on and talk a little bit about the great work you're doing.
Thank you. We appreciate your partnership with NASA and look forward to continuing to collaborate into the future. And thank you, students. You did an amazing job. I'm super impressed and very proud of how hard you worked and how well you presented. So thank you so much.
All right, thanks, everyone. See you next time.